Okay, everyone, welcome back to ELEC3204. So this course has three parts. The first two parts are about wireless radio frequency communication, and the third part is optical communication. This is also my first time to teach optical part of this course. So optical communication is not it's not really my area of expertise. So looking back, my teaching in the first part, I want to do two things differently in this optical part of teaching. The first thing is that I'm going to write more on the whiteboard when we have in-person teaching, and then for the recording, I will just show my handwriting on the screen. Because I found that especially in person teaching, when I write things down on the whiteboard, students tend to follow my thinking. So I'm going to do that a bit more. Secondly, I have designed a classroom game. It's based on a classroom quiz, but we are going to do a few activities. Hopefully, it would be fun, and it would improve our understanding of optical communication. So, okay. So first of all, optical communication is a very broad concept. It has been used for more than 2,000 years. For example, if you watch, for example, Game of Thrones, you'll see that when soldiers they signal attacked, they will flash a torch, and then all the other soldiers know that it's the time for attack. So historically, humans have been using light, torchlight, or smoke to convey a human message. So that is the origin of optical communication. And then the whole field was opened by Alexander Graham Bell. Has anyone heard of Alexander Graham Bell? So he's actually the inventor of telephone, and he also invented photophone. So photophone pioneered the creation of optical communication, a modulated sunlight to convey a voice signal. So Alexander Graham Bell, he invented both telephone and photophone, and on his deathbed, he said that he was more proud of photophone. So Alexander Graham Bell was a really important, very significant figure in the history of communication. So one of his biggest legacies is that he, in his lifetime, he started a company, and then the company was acquired by many big companies afterwards. But the essential part of the company is called Bell Lab. It still remains. It was acquired by AT&T in America for a while, and now it belongs to Nokia. So the Bell Labs is the most prestigious research lab in communication. It has generated quite a few Nobel Prize winners. So for example, all the multiple antenna technologies that we learned in the first part of the course they were all developed in Bell Labs. So that was the biggest, one of the biggest legacy of Alexander Graham Bell. And then we have the birth of cladding for optical fiber. So does anyone know what cladding is? So basically for fiber, we have core. So basically for optical fiber, we have core, and then the outer layer will have cladding. So these two different mediums, they have different propagation speed of light. So this would help to contain the light inside the fiber core. So fiber was a really important invention that would make light impossible to escape, or we want to contain light in fiber. So we don't want light to escape from fiber. And then in 1966, Sir Professor Charles Cowell, he invented glass fiber. So nowadays, all fibers that are manufactured by glass. The most significant thing about glass is that glass doesn't really, if it's pure glass, it doesn't absorb light. So but there is impurity in glass. So there is still going to be attenuation or loss here. So loss can be really low. So a fiber can expand really far. It can connect, for example, America and Europe. So for this, Sir Professor Charles Cowell received a Nobel Prize in Physics in 2009. So we did look at the spectrum before in the part of radio frequency. So basically, for all the signals, they have a frequency representation. So we have voice signal, we have visible light signal. So we can hear voice signal, we can see visible light signal. So all the signals that have frequencies higher than 2 kHz, we cannot hear them anymore. So we normally use the spectrum between here and visible light for wireless communication, so that wireless communication doesn't interfere with our everyday life. So conventionally, we have RF band here. We didn't use millimeter wave before 5G. So millimeter wave was dedicated to radar before, but right now the RF band has broadened. So basically right now everything under visible light can be used for RF. So I have started to use millimeter wave in 5G. In the future, we might also use terahertz and petahertz. So optical band here. In fact, when we talk about optical communication, we are using the spectrum here, which is different from the visible light. So this band cannot really be seen by human eyes. We still call it optical signal. This is because the generation of optical signal is completely different from the generation of RF signal. So for RF signal, it is more electricity centric. And then for optical signal, it's generated based on the photon theory of light. We'll talk more about both of them a little bit later. So I'm not sure if you remember that in the first part of teaching, we discussed why we didn't use millimeter wave before 5G and why we start to use millimeter wave. So first of all, rule of thumb, as frequency increases, we would have more available bandwidth. So we want to use higher frequency band. However, another rule of thumb, as frequency increases, the antenna aperture, so the antenna size, would become smaller. So in the past, it's very hard to manufacture. But in the era of 5G, we can manufacture this antenna for millimeter wave. So in the future, we are also going to use terahertz and petahertz. So all the spectrum up to visible light, they don't have ionizing radiation. So for the spectrum above visible light, there will be ionizing radiation, which will be harmful to our body. So we use the frequency band below visible light and above voice for communication, so that first, it doesn't interfere with our everyday life, and then secondly, it doesn't harm our body. There is no ionizing radiation. So before moving on, we need to discuss a question, which is here. So if it's in class, in person teaching in the classroom, I would have written all of this on the whiteboard. So basically, this question is, what is light? So as I said before, light is a very broad concept. It's not restricted to the spectrum of light that we can see by our eyes. So the first theory that can describe light is the ray model, where we know that when the signal is propagated from one medium to another, there will be reflection and there will be refraction. So refraction is also called transmission. So we have Snell's law that tells us the direction of reflection and refraction. And we have a Fresnel formula to tell us the strength of the reflection. But there is limitation of the ray model. The ray model cannot explain diffraction. So we need a second model, which is electromagnetic wave model. So EM wave model. So when a light propagates towards a slit, it would pass a slit and continue to propagate as a wave. That leads us to the famous Young's experiment, where we have a light source here, and then there are two slits on the wall, and then so after these two slits, we have two coherent waves that aid together constructively at the distance of magnitude of wavelengths. So if I have like a wall here, what we will observe is a strip of darkness and strip of light, and then strip of darkness, and then strip of light. This is because from the two slits to a darkness strip, the difference in the distance is magnitude of half of the wavelength. So two waves would aid together destructively. They will cancel each other. And for a light strip, the distance difference between the two slits would be magnitude of a multiple of wavelengths. So the two waves they aid together constructively. So for the EM wave model, we have Maxwell's equation to describe the EM wave propagation. But EM wave propagation also has limitations. It cannot explain the photoelectric effect. So we need the photon theory of light. So for the photon theory of light, for example, when we have an electron here, it is on a low energy state. It is on a stable state. So normally electron is orbiting an atom. So it is orbiting an atom at a low energy state. And then if we charge the electron will move will be stimulated to a high energy state. But high energy state is not stable. So eventually the electron will give up its energy, and the energy has to go somewhere. So the energy become light. The energy is a photon. So basically we have Planck's constant that tells us the relationship between the energy given up by the electron and the wavelength of the light. However, the photon model of light, the photon theory of light, also cannot explain everything. It cannot explain Young's experiment, because if we consider one photon as one particle, then one photon cannot really pass through two slits at the same time. So that is So that is a limitation of the photon theory of light. So in summary, what is light? So in some scenarios, it's one of them, one of the three models. In some scenarios, it's all of these models. It is also possible that it's none of them. So in the future, it is possible that in science, we will have another theory that can explain everything. We do not need these three models anymore. So what do we really know beyond our knowledge, high school knowledge? Not actually a lot. What we try to do only is to try to make breakthroughs in small areas, but in big picture, we do not really know a lot more than our high school knowledge. So interesting thing about the photon theory of light. Oh, I'm not sure if anyone knows who created the photon theory of light. So it's Albert Einstein. So when he developed the photon theory of light, it wasn't well accepted by the science community. So he wanted to become a fellow of the Royal Society of Germany of that time. So it was Prussian. So he asked one of his colleagues to write a reference letter for him. So that colleague wrote something like his photon theory of light should be excused. Should be excused. So it simply just means that his photon theory of light is ridiculous. It was considered ridiculous at that time. But actually, I actually won him a Nobel Prize 10 years later. So at this point, I would instruct the class to play a classroom game, to do some activities. So for example, if this is the classroom, and this is where the whiteboard is, so I will be in front of the class, and we have a group of students sitting in this area. So we will try to mimic reflection, refraction, so the ray model, for example. So what I would do is I would throw a lemon to a random student somewhere in the middle. And when we do reflection, the student should forward a lemon to another student in one of the front rows. And if we practice a refraction, then the student should forward forward the lemon to someone in the back row. And then here I ask a question, what is critical angle? This is something probably we have all learned in high school, but some students are more familiar with it because they take a photonics class at the university. So critical angle happens when this angle becomes larger and larger, and then this angle becomes smaller and smaller. Eventually, there will be no refraction anymore. There will be no refraction. So when this angle increases up to critical angle, there will be only reflection. So when we practice a critical angle, the student should only forward the lemon to someone in one of the front rows. We are going to do more exercise like this. We are going to learn from action about a coherent wave, and we are going to learn about intelligent surface, etc. So from this propagation, from this lemon, so if you consider lemon to be a photon, it kind of makes sense of the photon theory of light, and the direction of the lemon's trajectory makes sense of the ray model. And if we throw a lot of lemons, then there will be energy towards reflection, energy towards refraction. So it kind of also makes sense of the wave propagation. So we'll talk more about all of them later on. Let's come back to the slides. So we have looked at the spectrum, and I mentioned that the signal generation of RF, so the transceiver design of RF, so this is optical band. The optical signal generation and the reception is completely different from the RF systems. So we're going to talk more about this here. So this is a RF system. So what we normally do is we do everything modulation, signal processing in the baseband. And then we modulate the baseband signal to a RF carrier. So what is this? This is a mixer, MIX ER. So basically, this mix the baseband signal with RF signal, so that the signal will be transmitted at higher frequency band, which is defined by FRF. So FRF is also called carrier frequency, kind of carries signal. It's a higher frequency band. And then as a receiver, we do down conversion back to baseband, and then we do the symmetric signal processing, and then get the information. So optical system is completely different. So as I said before, there is actually only one way to generate light, which is we need to stimulate electron. And then when electron give up its energy, it will produce a photon. It will emit light. So this is the only way to generate light in reality. So we have optical conversion here, and then we have the optical source, and then it is transmitted through a medium, so fiber, and then at the receiver, we have the optical electro conversion. So the biggest limitation here is the conversion between electrical domain and the optical domain. So fiber can carry very large bandwidth signal, but the conversion here cannot modulate that high bandwidth. So normally the fiber can support transmission on the order of T hertz, but the modulation bandwidth normally is on the order of less than 100 gigahertz. So this is a major limitation. But in this way, the deployment of fiber is also beneficial because fiber itself is future-proof. In the future, if we improve the transceiver, we just update the transceiver. We do not need to change the medium because we are still very far away from the data rate that can support it by the medium. So we have different transmission media. So for the wireless communication, we have wireless channels. So there is a transmitter, there is a receiver. We have line of sight. We also have a lot of reflections. So why? So question here is that why we don't use optical signal for wireless communication? This is because the optical signal in free space would attenuate a lot, so it wouldn't propagate far. But RF signal would propagate a lot further than optical signal in free space. But in fiber, on the other hand, light can propagate very far. It can cross continents. So we use light we use optical communication in fiber, and because optical signals they are at higher frequency spectrum, so I have more bandwidth there. So we use fiber to guide optical signal for long distance wired communication. So for wired communication, conventionally we also have copper cable, and now we have upgraded them almost all of them to optical fiber. So basically, optical fiber is safer. You can deploy it next to, for example, a lake. You don't need to worry about leakage of electricity because it's only light in the fiber. So it's safer, and the bandwidth is higher, and it's more green because the generation of optical signal should consume less electricity. We do not generate kind of carrier frequency and then use a mixer. What we do is stimulate electrons, and then light is generated. Okay, so there are some advantages here. So basically, fiber has high data rate, high immunity from, so it's separated from the RF band, so it doesn't interfere with the RF band. And then it has high temperature tolerance, and also it's safer, it's smaller and lighter. So what is the biggest challenge? So as I said earlier, the biggest challenge is that the generation of light here has limited modulation through bandwidth, which is normally on the order of less than 100 gigahertz. But here we can support THz. So the biggest challenge is here. We continue to improve the modulation and modulation systems. The fiber itself is future-proof. Okay, there are other challenges. For example, cost. So it kind of trade-off between single mode and multi-mode fiber, and also LED and laser. So LED would be cheaper, and then laser would be more expensive. We'll talk more about that in future lectures. So there is also, so loss is also called attenuation. So we have attenuation in wireless communication as well. So when signal propagates over distance, the signal power would attenuate. So for fiber, it's the same. So chromatic dispersion. We'll talk about this quite a lot. So basically, what happened here is that for any light source, we have a collection of wavelengths. It wouldn't be just one wavelength. We'll have a collection of wavelengths, and different wavelengths, they would travel at slightly different speed. So as a transmitter, we have poles, separated pulses. And then after long distance transmission, the pulses would overlap. So here we have inter-symbol interference. So why we didn't have this in RF? The chromatic dispersion is in RF. This is because for wireless communication, the propagation distance is very small. For example, a base station can cover a campus. So for that distance, the different light speed for different wavelengths do not show. It doesn't show. It doesn't show any effect. So we do not observe chromatic dispersion for radio frequency communication, wireless communication. However, in wireless communication, we have similar dispersion effect. So we have a transmitter, we have a receiver, we have a line of sight, and we have a lot of reflections. So this is multi-pass. So each pass would have different delays and phase rotation. They arrive as a receiver, uh, uh, sometimes aid together constructively, sometimes aid together destructively. So how do we represent this multi-pass in time domain? So this multi-pass would introduce inter-symbol interference. So chromatic dispersion would also introduce inter-symbol interference. So how do we represent inter-symbol interference mathematically? So for example, if we transmit one symbol, and then it goes through a channel, there is probably noise. And then we receive one symbol. There's basically no inter-symbol interference. However, if I have multiple copies with different delays for RF, and then for optical, we have different wavelengths, they travel with different speed, so they arrive as a receiver with different delays. So what we have is we receive a symbol, which is summation of all the delayed signals with their fading element. So this would introduce inter-symbol interference. So how do we mitigate inter-symbol interference in wireless communication? We mitigate this by using OFDM. This is because the convolved product here. So this is like a convolved product between H and S. So convolved product in the time domain would be just simple one-tap product in the frequency domain. That's why we use Fourier transform, and we modulate signals in the frequency domain so that we do not encounter the inter-symbol interference in the time domain. Okay. So there's also polarization mode dispersion. So EM wave have electric field and also magnetic field. Different waves, they would have different polarization, and different polarization would have different propagation speed. So if different elements of the wave, they have different propagation speed, then as a receiver, they would have different delays. So this would cause inter-symbol interference. Also, optical non-linearity. For example, if the medium is not pure, there's impurity there. Then there's non-linearity in the fiber. So all of these are challenges in optical communication. So as I mentioned earlier, chromatic dispersion is a very key this challenge of optical fiber. So it happens when the light source have a wide of wavelengths, and different wavelengths, they would travel at different speed. So as a transmitter, the pulses we transmitted are well separated. And then after a certain distance, the pulses, they will overlap. So now we have inter-symbol interference. We'll talk more again about this in future lectures. Okay, so this is an example of fiber. So about 10 years ago, for example, Google's, this is Google's data center. Is inside of Google data center, they used to use copper cable to convey data, but it consumes a lot of electricity. So it consumes a lot of electricity. So nowadays, they have all been replaced by fiber. So the optical transmission can also be very, very local. So this is a single chip communication using light. This is a really interesting and very important breakthrough that happened in 2015. So it's not very long ago. So basically, when we have a chip should perform like CPU calculations. So what we do here is we generate light transmitter. So we have a light transmitter, we have a light receiver. We use light to perform calculation. How do we do that? So if you, so first of all, we know that when light is transmitted towards a surface, we know that when light is transmitted towards a surface, there will be reflection, there will be transmission. So basically, when light propagates through surfaces, it will introduce phase rotation to the light. Do you remember what is Fourier transform? Fourier transform essentially is a series of phase rotations. So if we have a transmitter here, we have a receiver here, and then we have a series of materials. So when light propagates through these materials, it can perform Fourier transform. So what is the advantage of doing this? The first advantage is that the calculation can be executed at the speed of light. That is very attractive because the calculation would be really, really fast. The second advantage is that instead of calculation based on electricity, this would cost less electricity. So it can help us to better achieve the carbon neutrality goal. So optical communication can be really, really local. It can also be very long distance. It can connect USA and, for example, America and Europe. Okay, here's a reading list. There are 3 books. They can all be found in library. So another very important thing we need to learn today is what is phase. So basically, phase. What is phase? Phase characterize periodic function. So how a periodic function propagate as wave. So if you think about water wave here, the wave would propagate over distance, so it would come towards shore. And if you look at one point, one location, then the wave would change, would vary over time as well. So basically, wave would propagate over distance, and wave would vary over time, 2 directions, time and distance. So if we look at a periodic function, which is a sine function here, the first reference is just a simple sine wave. The period is peak to peak, which give us 2 pi. So the period is also from 0 past first crossing and then come back to 0. This is also 2 pi. And then we are interested in how a wave propagates over time. Over time, so t here is a time variable. So here from peak to peak, we have also traveled 2 pi in angular domain. But it has taken us t seconds. So t is a period in time domain. So we have omega here, which is also called angular frequency. It tells us how fast wave propagate over time. So the third domain is distance. So wave also propagate over distance. Um, so once again, peak to peak, we have 2 pi. And then over one cycle, we would have traveled a wavelength of distance. So the metric of wavelength is meter. And then we have a parameter here, propagation constant, which defines how fast wave propagate in distance. So let's have a brief summary here to enhance our understanding. So I would have written this on the whiteboard. So you can see that first of all, the topic here is what is phase. So the first simple example is a simple sine function. So phase characterize how a periodic function propagate as wave. So for a simple sine function, the only variable is a phase. And then the first crossing is half of the period, pi here, the first crossing. And then the period is 2 pi. And this whole thing is in angular domain. We are interested in how wave propagate over time and over distance. So over time, the variable is t. And then from peak to peak, we have traveled 2 pi, but it costs us t seconds. So we have t as period, and t equals 1 over frequency. So we also define the parameter of angular frequency, which tells us how fast wave propagate in a time domain. And then the third, and then in distance domain, we have kz. So the variable is z. It has a unit of meter. So over one period from peak to peak, we have also traveled 2 pi. But the wave would have propagated over lambda a wavelength of distance. So the period is wavelength. You can see how these two are related. So one cycle of 2 pi takes t seconds and travels a wavelength of distance. So the speed of light is here. So basically, the wavelength is time multiply the speed of light, and then we have traveled a wavelength. So the parameter here is the propagation constant, which tells us how fast a wave propagates over distance. So this is a very important concept. Okay, let's come back to the slides. So once again, wave propagation is like water, where it would propagate over distance and it would also vary over time. So for EM wave, we basically the wave would propagate over time and over distance as well. We have two directions. So what is omega? Omega is angular frequency that tells us how fast the wave propagates over time. So if the distance, the location is fixed, then we have only the propagation over time. What is K? K is a propagation constant that tells us how fast the wave propagates over distance. So at any, if time is fixed, then wave would propagate only over distance. Okay, so light is an electromagnetic wave. This means we have electric field and we have magnetic field. Okay, and the electric field and magnetic field, they oscillate in phase, which means they peaks and nulls at the same time, and they are oriented at 90 degrees to each other, so they are orthogonal to each other. And also, the electric field and magnetic field, they are transverse to the propagation direction. So what is polarization? So basically, we have direction of the electric field and we have the direction of a magnetic field. So if we define for all the components in a light, for all the wave components, if we align their direction of the electric field, so if all of them share the same direction, then we call it polarized light. If it's random, then it's unpolarized light. So what is interference? So two waves can interfere. So we have two waves with field A and field B, and they act together constructively. They peak at the same time, and then crossing at the same time. So the overall magnitude become bigger. Interference can also be destructive. So the two waves, they are completely out of phase. So the overall sum is 0. And then sometimes it's somewhere in the middle. They are neither completely in phase nor completely out of phase. So it's somewhere in the middle. So there are two preconditions of interference. First of all, the two waves, they should be aligned in terms of polarization. Ideally, all the wave components, ideally, all the wave components, they should have the same direction for the electric field, so that they will act together. If two waves, they have orthogonal direction, they wouldn't act together, they wouldn't interfere. If two directions, they are of an angle to each other, that is not orthogonal, then the projection of the first wave would interfere with the second wave. So the second condition is coherent. Coherent wave means that the phase relationship have to be constant. It doesn't mean that we have to have constructive interference. It means if we have, it can be constructive, it can be destructive, it can be intermediate. It just have to be constant. So if it's constructive, it has to be constructive all the time. If it's destructive, it has to be destructive all the time. So we will do a practice here. So there is also another question: what is partial coherence? What is incoherent wave? So in the classroom, I would find two rows of students, and then I would give one student at this end, so both students at this end, I would give them both a lemon and ask them to pass at any speed they like. So the lemon would pass on to other students until the lemon reach this end. So this is incoherent wave. The two waves, they are not periodic at the same time. They are incoherent, they wouldn't act. So what is coherent? So if I give two students here two lemons, and then I ask them to pass on lemon to the next student, only when I clap. So I would clap periodically, and then the two rows would pass lemon at the same speed. So this is a coherent wave. So one wave, so a single wave can be coherent as well. So for one wave, we can say this wave is coherent to itself when the beginning of the wave and the later part of the wave share the same periodicity. So, for example, if I give a student a lemon here, and then at the beginning I clap periodically, and then after a while I stop clapping, and then the students afterwards can pass on the lemon at any speed they like. So at the beginning there's periodicity, and later on the speed has changed. So this is partial coherence. At the beginning it is periodic, and later on it is not. It does happen because different wavelengths, they have different speed. So at the beginning, different wavelengths, they travel at relatively the same speed. So they share the same periodicity. They are coherent waves. But later on, their difference in speed would become a bigger problem. Okay, so here's a summary of today's lecture. So I will do a class quiz. So what I would do here is that I would randomly throw a lemon to different students. So whoever catches the lemon should answer a question true or false. So the first question, the EM wave model describes that light propagates in two domains and two fields, true or false. So this is actually true because we have two domains, time domain and distance. We have two fields, electric field and magnetic field. Second, fiber is made by glass that is the same as window glass, true or false. So this is actually false because when we manufacture fiber, we increase the temperature and make it liquid. And when we reduce the temperature, there is no clear transition from liquid to solid. So fiber can bend, but the window glass, it cannot bend. So we cannot actually deploy window glass across Atlantic. The third question, light waves that are not polarized in the same direction do not interfere, true or false. So this is actually false. So ideally we want two waves to have the same polarization. If they are orthogonal to each other, they wouldn't interfere. But if they are not polarized in the same direction, but they are of a certain angle that is smaller than the orthogonal angle, then the projection of the first wave onto the second wave would interfere with the second wave. The fourth question, incoherent light waves do not interfere, true or false? So this is true. So if two waves, they are not of the same periodicity, they wouldn't interfere. Fifth, interference is a negative effect because power can be lost, especially when we have destructive interference, true or false. So this is actually false. In physics, interference is a neutral term. When there is destructive interference, the power at this location is zero, but as the power would simply go to other places. It's not lost. For example, if we look at Young's experiment again. So if we look at Young's experiment again, on the wall, there will be dark strips and there will be light strips. So on the dark strips, the power would be 0. So power simply transferred to the light strip. So, okay, that's all for today. Yes, that's all for today.